Hi, everybody. At this time, toward the end of the term, I was hoping that maybe we could take a little bit of time and look at some of the few recurring themes in the history of math. We want to make sure that we don't miss them. This is something that's important for us and our teaching. And the first thing that we want to remember is that notation is everything. Now, we talked about this in an earlier video. Another recurring theme is that the pursuit of knowledge for knowledge's sake, without any promise of practical application, is not a waste of time. Oftentimes, applications come unexpectedly after the knowledge is gained. A third recurring theme is that oftentimes a diverse academic background is the key to acquiring knowledge and producing applications. And a fourth recurring theme is that most, if not all, of the great mathematicians of antiquity traveled throughout the known ancient world. So let's take a look at these things one by one and just make sure that we can milk all of these observations for all that they're worth. Let's take a look at the first one. I hope this is the first one. We had a remark in one of our first studies that said we should take note of the fact that something as seemingly arbitrary as notation would turn out to be so indispensable in enabling the Babylonians to make giant strides in mathematics, and that a poor system of notation almost certainly prevented the Egyptians from doing the same. And I believe there's a message here for our students, many of whom typically think that how they write their work and document their work is irrelevant and should be left strictly up to them, a matter of personal choice, just a matter of taste. This historical example may come in handy in convincing our more submissive students that there are sound reasons why they should do things our way, the conventional way, instead of doing things their way. And armed with this fact, we may want to encourage our students not to let lack of good notation prevent them from making giant strides in mathematics. Notation is everything. Now let's see if we can go to the next slide. We learned about Diophantus. His text was called Arithmetica. And I guess there should be a T in here, huh? An assortment of 189 problems along with their solutions. The question was, how could we describe Diophantus' main contribution to mathematics? And what is the name of the text that contains his work in this area? Well, the text was called Arithmetica. And here it says Diophantus' main contribution, referred to as syncopated algebra, was a system of algebraic shorthand used to denote such things as exponentiation, equality, subtraction, and reciprocals. And the remark here, once again, note that something as seemingly arbitrary as notation would turn out to be so indispensable in removing roadblocks and enabling mathematicians to make great gains. Hence, there are sound reasons why our students should do things our way instead of doing things their way. Armed with this fact, we may want to encourage our students not to let the lack of good notation prevent them from making giant strides in mathematics. Notation is everything. Another example, what was Francois Vieta's innovation and how did it help to further the study of algebra? And the answer was, Vieta's innovation was using consonants to represent constants, known quantities, and vowels to represent unknown quantities or variables. This made it possible to solve an entire class of equations at one time, an entire class of equations at one time. Now, we often use a modified form of this practice. We use letters at the beginning of the alphabet, for example, A, B, and C, to represent known quantities, and letters at the end of the alphabet, X, Y, Z, to represent unknown quantities. This makes it possible for us to solve an entire class of equations at once. And hopefully a very familiar example pops up. The best example is the solution of the generic quadratic equation, ax squared plus bx plus c equals 0, has the solution x equal negative b plus or minus square root of b squared minus 4ac over 2a, the quadratic formula. This provides the solution or solutions, I'll put solutions for all quadratic equations. And again, notation is everything. One more thing to look at as far as notation goes. Later in our studies, we had this question: what explanation is given for the drastic increase in mathematical achievements during the 16th and 17th centuries? And the answer was, in part, the introduction of the symbols for addition, subtraction, equality, multiplication, division, less than, greater than, less than or equal to, greater than or equal to name a few, as well as a way of representing exponentiation. All of these things, it says, facilitated algebraic manipulation. For example, imagine how hard it would be to solve a simple problem if there were no such thing as an equal sign. There would be no equation axioms. For instance, we can add any real number to both sides of an equation and the solution set remains the same. We can subtract any real number from both sides of an equation and the solution set remains the same. We can multiply or divide both sides of an equation by any non-zero real number and the solution set remains the same, et cetera, et cetera. There would be no inequality axioms. For example, we can multiply both sides of an inequality by any positive real number, and the sense of the inequality remains the same. If we multiply or divide both sides of an inequality by a negative real number, the sense of the inequality is reversed. If we didn't have an equal sign or inequality signs, we wouldn't have equations and inequalities. There'd be no equation axioms. There'd be no inequality axioms. We'd have nothing. Notation is everything. And motivated by these historical examples, we should convince our more submissive students that they should do things our way, the conventional way, instead of doing things their way. Okay, let's go to another class of documents now. Hopefully this is the one that I want. Well, maybe not. Let me look at this one. Okay. Here we have a question. What allowed the Greeks to progress far beyond their Babylonian and Egyptian predecessors in mathematics? There are a couple of factors at work here, but let's look at the second one right here. Prior to the golden age of Greece, learning and knowledge have been largely monopolized by powerful priesthoods and the educated elite in order to preserve their power and influence. In contrast, the Greeks considered the pursuit of knowledge to be the right and duty of all citizens. Knowledge for the sake of knowledge. That was a new one. The Greeks introduced us to that concept. Let's continue on this tack. What factors made the museum the center of learning in the Hellenistic world? The leading scholars of the time, scientists, poets, artists, writers, were invited to Alexandria by the Ptolemies and given living accommodations as long as they wished to stay. They had leisure time to pursue their studies, access to the finest libraries, opportunities to discuss matters with other resident specialists, and were given generous salary stipends. And what did they have to do to get this? The only condition imposed on the lecturers of the museum, they had to give regular lectures, and regular meant perhaps once a year, regular lectures on the topics of their choice. And what was the main purpose of the museum? To serve as an institution for research and the pursuit of learning. The sponsorship of these scholars was not contingent on the promise of practical applications. Notice that. That's a huge point here. A third thing that we want to look at, what observation has been made about the 200-year period during which the museum was at its height? In the history of mathematics, there's only one other span of about 200 years that can be compared for productivity to the period from 300 to 100 BC, namely the period from Kepler to Gauss. And here's a remark. The scholars at the museum were free to choose their course of research. Their choices were not restricted to areas or projects that showed promise of a practical application. And yet only one other 200-year period in history compares with this period during which the museum was at its height. And the point of all of this is that a course of study need not have an obvious application in order to be beneficial. And historically, it's often been the case that research gave birth to applications rather than the other way around. Similarly, just because our course instruction appears to students and parents to be lacking practical value or application does not mean that it lacks merit. And I have a few thoughts on this that I would like to put forth now. A course of study need not have an obvious application in order to be beneficial. Historically, it was often the case that research gave birth to applications rather than the other way around. And similarly, our course of instruction may appear to students and parents to lack any practical value or application, but that doesn't mean that it lacks merit. And this is important because oftentimes both parents and students take a dim view of education, and especially toward those disciplines that require a measure of effort and self-discipline in order to succeed. In an age when people in general are disrespectful of authority figures, it's not unusual for both parents and students to try to trivialize the value of mathematics and those who teach it by saying such things such as, when are we ever going to use this? What does this have to do with the real world? And so forth. Now, it'll be to our advantage to be able to explain to them that oftentimes applications come only after the knowledge has been gained. And we can use the example of a parabola. What is a parabola? It's the set of all points in the XY plane that lie equidistant from a fixed point, the focus, and from a fixed line, the directrix. Some 2,000 years ago, the ancient counterparts of today's parents may well have asked, when are we ever going to use this? What does this have to do with the real world? And so forth. Well, during that time, in ancient times, it was discovered that if parallel rays strike a parabolic surface, the rays are reflected back to a single point, the directrix. And again, the ancient counterparts of today's parents and students might have asked, so what does that prove? What does this have to do with the real world? When are we ever going to use this? Well, legend has it that a giant parabolic mirror was used in the defense of the city of Syracuse against Roman invasion. As Roman ships came into the harbor, this giant mirror would focus the sun's rays on the ship and set the ship afire. Now, some say this is legend, some say it's fact. We don't know for sure. But remember, until the late 1800s, it was thought that the ancient city of Troy never existed until an archaeologist named Heinrich Schliemann discovered its ruins. So some people say that this event never occurred. Others do. We don't know for sure. But there were parabolic mirrors of this sort that were used in the defense of Constantinople in the year 514. So they did find a powerful application in defense, even though at the time of the inception of a parabola, there was no application being sought. It was just knowledge for knowledge's sake. And parabolic mirrors, so to speak, have been in common use for about the last 100 years. We use them as the receptors of electronic signals. What's the expression people use? Radar dishes. Okay. The communications industry today would be nothing if it weren't for these parabolic mirrors, so to speak, that gather electronic waves and channel them to a single focus point. And yet, 2,000 years ago, the study of parabolas seemed pointless. It showed no promise of any practical application. And this is often the case in mathematics. And even if no practical application ever comes from a particular salute, that doesn't mean the pursuit is of no value. And at this point, an analogy might be useful. Football players have to work out in the weight room. They have to do squats. They have to do bench presses. They have to do deadlifts. Now, we never hear the players trivialize this training as being nonsense and saying, when are we ever going to have to do squats and bench presses on the football field? What does this have to do with the real world? When are we ever going to use this? When are we ever going to have to do squats and bench presses in a football game? And they're never going to have to do any of these things in a football game, and they know this. But they also know, and here's the point, that this type of physical training will enable them to perform at a much higher level on the football field. And similarly, many of our students may never have to do something like completing the square after they get out of our class. But this type of mental training and mathematical training and exercise will enable them to perform mentally at a much higher level throughout their life. So even if no practical application ever comes from some of the things that we cover, that doesn't mean that this pursuit is of no value. Our students are going to benefit from it one way or another throughout their entire life. Okay, let's go on to the next screen. What early life experiences prepared Thales for a prodigious mathematical career? And the comment was during his early years, he had commercial ventures that led him to travel extensively. In his travels, he learned geometry from the Egyptians and astronomy from the Babylonians. Okay. A recurring, well, let's see, I'm not done here, am I? No, I don't think so. What early life experiences may have prepared Pythagoras for a prodigious mathematical career? He left home in Samos as a young man to study in Phoenicia and Egypt, and may have also studied in Babylonia. After years of extensive travel, he settled in Crotona in southern Italy. And we have one more. What is known of Fibonacci's background? Fibonacci, also known as Leonardo of Pisa, was born in Pisa in 1175 and educated in North Africa, where his father was in charge of a customs house. He traveled extensively throughout the countries of the Mediterranean as a young man, studying the arithmetic systems used in the commerce of different countries. During his travels, he recognized the advantages of the Hindu Arabic number system with its positional notation and symbol for zero. Okay, this is a recurring theme in the history of math. Many of the prodigious mathematicians of antiquity traveled extensively, especially during their younger years. And this travel played a significant role in their mathematical development. Now, what does this have to do with us as math teachers? We might be mindful of this when some of our students show an interest in well-chaperoned study abroad programs. If the interest is there, but they're a little bit hesitant, we might want to offer them encouragement based on this observation. And I will add a caution here. My words were somewhat carefully chosen. I said well-chaperoned study abroad programs. So we don't want 500 students and 2 chaperones. But when there are a healthy number of chaperones given the number of students, like maybe 1 chaperone for every 2 students or something like that, and they have a study abroad opportunity, we definitely might want to encourage them to check this out. And let me share one more thing with you. What 4 principal areas of study did the Pythagoreans engage in? Arithmetica, number theory; harmonia, music; geometria, geometry; astrologia, astronomy. You know, it's interesting that as mathematicians and scientists, music would be part of their training. It was part of their training, and it was considered to be a very important part of their study as well. So that's interesting. These mathematicians weren't just interested in arithmetic, number theory, that is, and geometry, but they were also interested in astronomy and music. Astronomy, well, it's a science, kind of a hard science. We might see mathematicians being interested in that, but music, the Pythagoreans insisted on it. And they were definitely students of music, and they approached it as an art and as a science. And there are a few points here. The first point here is that our students benefit did I cut that off too soon? I don't know. Hold on a minute. I'm going to share it again anyway. That's not the one I want. Please forgive me. Bear with me. I think that's the one I want. Yes. Uh, let me move on to a second point closely related to this. 4 principal areas of study the Pythagoreans engaged in. Music was one of them. Astronomy was another. Really, mathematicians studying those things? Well, let's take a look at something else here. In what fields of study did Eratosthenes excel? Look at this: geography, philosophy, history, astronomy, mathematics, literary criticism, poetry. He was a mathematician, but he studied all of these other areas as well. He wasn't considered a top mathematician, but he was considered enough of a scholar in each of these fields to be the head of the museum in Alexandria. He was essentially the director of all studies at the museum in Alexandria. And let's look at his contributions to geography. What was noteworthy about his 3-volume work, Geographica? First scientific attempt to put geographical studies on a sound mathematical foundation. Also, he discussed the arguments that applied that the Earth was spherical. He described the positions, given the assumption of a spherical Earth, of various land masses of the known world. And he was the first to use a grid of longitudinal meridians and parallels of latitudes. Okay. Now, the point here is that our students benefit by being exposed to and educated in a number of different areas. And they don't even have to be closely related. But we consider Eratosthenes as an example. Look at this: geography, philosophy, history, astronomy, mathematics, literary criticism, poetry. That's quite a diverse range of studies. But the notion of a spherical Earth may have occurred to him during his studies as a historian. He may have realized that some of his predecessors a few centuries earlier believed that the Earth was spherical. His background in astronomy, no doubt, made the idea of a spherical Earth plausible, and may have even made the idea a certainty in his mind. Being a mathematician, he was able to devise a simple practical experiment and calculate with the experimental data the circumference of the Earth. He came darn close. I think his estimate was around 25,000 miles and just off by a few hundred miles. So that was an amazing feat, especially considering the time that he was living in. His background as both a mathematician as a geographer, mathematician and as a geographer, certainly allowed him to come up with the notion of a geographical grid of longitude and latitude on which to plot the land masses. Whereas somebody who was a mathematician but not a geographer couldn't have done this. Someone who is a geographer but not a mathematician couldn't have done this. A person would have had to have been both a mathematician and a geographer to devise this clever scheme. And we look at the system of longitudinal lines and latitudinal lines, and we think, yeah, what's the big idea? Well, you know what? Think about this. The lines of latitude and longitude on a map, do they remind us of something that we use quite a bit when we do math today? Think about it. Perhaps maybe they remind us of the XY coordinate system. Think about it. The horizontal lines correspond to Y values. The vertical lines correspond to X values. Latitude and longitude, right? And yet, even after Eratosthenes created maps with lines of longitude and latitude and these came into common use, it took mathematicians another 1,800 years to come up with the idea of the XY coordinate plane. So this was definitely a stroke of genius on Eratosthenes' part. He would have had to have been an expert both in math and in geography to do this. And this supports my position that it may be a great advantage to students to study not just in one area, but in several areas. Today, I guess we call these interdisciplinary studies, but this is not a bad idea. And I'll tell you a story of a friend of mine. He worked on small engine repair. He also did automobile repair, engine repair, anything having to do with automobile mechanics, small engine mechanics. And he knew his way around a machine shop fairly well. This guy went to college and decided he was going to be an electrical engineer. And I thought, duh, electrical engineering? The guy understands mechanics. He's got a really great grasp of that. Why not be a mechanical engineer? Hello. But for some reason or other, he decided to be an electrical engineer, perhaps because his father was an electrical engineer. Well, you know what? When he got done, he knew more about mechanical engineering than any electrical engineer ever knew. And he knew more about electrical engineering than any mechanical engineer ever knew. And he was in the right place at the right time for the advent of the science of robotics. Robotics is essentially a marriage between electrical and mechanical engineering. And he was in the driver's seat. He's been designing robotic hands and grippers for about 40 years now. And again, it was his knowledge of mechanical and electrical engineering, plus the fact that he knew his way around a machine shop and he knew what machinists could do. That those interdisciplinary studies, so to speak, made him a leading figure in robotics because he had that diverse background. He could conceive of things that no electrical engineer could conceive of. He could conceive of things that no mechanical engineer could conceive of. And he knew exactly how to implement these things because he knew what machinists could do. So as far as not just focusing on math, but maybe a number of areas, and they don't even have to be closely related, this can be a very good thing. For example, the study of mathematics and the study of foreign languages, Latin, Spanish, French, not a bad idea at all. So having a diverse area of study is not necessarily a bad thing. I did have another friend who is a mathematician who spent quite a bit of time studying biology and got a master's degree in biology. Well, you know what? There's a lot of work being done now in the marriage of those two fields. So as far as interdisciplinary studies go, that's something that we might want to recommend to our students, especially if the interest is already there. If they have an interest in two diverse things, let's say music and mathematics or music and engineering, wow. Just think about what the last 30 or 40 years have been like in the music industry. If you don't know engineering, recording engineering, electrical engineering, you're not going to be able to do much in music. So, interdisciplinary studies, studying things that don't seem to be closely related. If our students have an interest in that, we might want to nurture that interest. A second point, and this is a good point, is that whatever genius Eratosthenes had was augmented by his creativity. And you know, uh, Eratosthenes was not highly touted by the mathematicians of his age. He was a good mathematician, but they didn't consider him to be a great mathematician. You've heard the term alpha male. Well, you know what his colleagues called him, and this is a true story. His colleagues called him beta. And it's in exactly the same context as alpha male or alpha mathematician. They referred to him as a beta mathematician. Not really up to snuff with all the other top mathematicians of the day. And yet, do we know who most of these mathematicians were that held him in derision? No, apparently none of their contributions are remembered in history. Maybe they weren't all that important contributions. On the contrary, Eratosthenes was known for a number of contributions. And here's something that is probably the reason, and that is what genius Eratosthenes had was augmented by his creativity. You know, some people who are genuinely brilliant and extremely quick to understand even the most complicated topics may not possess much in the way of creativity. Yeah, they're genuinely brilliant, but they may not produce as much as someone, they may not produce as much as we would expect somebody with their brilliance to produce. On the other hand, some people of modest genius are also quite creative and inspired. Apparently, Henry Ford was one of these guys. Not a real genius, but boy, he had an imagination. And although people like this are not as quick as their peers to fully grasp a deep topic, they seem to be able to think of things and come up with ideas that no one else would ever think of. Their genius is augmented by their inspired creativity. And you know what? Standardized tests don't reveal creativity. Our students may not score in the top percentiles of standardized tests, and yet they might have quite a future in front of them because of their creativity. So if our students are good, but not brilliant, there's still a niche for them in mathematics as long as they do their best. And let me go to the last slide here. What tool for use in number theory may be considered Eratosthenes' most significant mathematical contribution? The sieve of Eratosthenes. This he constructed by listing the integers from 2 to n, and then removing all multiples of each prime number except for the prime itself. And what we're left with is a list of all the prime numbers greater than or equal to 2 and less than or equal to n. It's a foolproof way of doing it. Did it require brilliance? No. Any mathematician back then would have understood what was going on. But did it require creativity? Must have. Nobody else thought about it. He did. He was the only one that came up with that idea. For what mathematical geographical contribution is Eratosthenes best remembered today? Devising a practical and simple method for calculating the Earth's circumference. You know, part of the genius of Eratosthenes was his simplicity. This is an experiment that actually a class of high school students could carry out. Let me rephrase that. This is an experiment that 2 classes of high school students could carry out. One class in one location and another class about maybe 500 miles due north of that. 2 teachers would have to coordinate this, but each class could gather their own experimental data and reproduce the experiment that Eratosthenes conducted, and measure the circumference of the Earth themselves. Part of the genius of Eratosthenes' scheme to measure the circumference of the Earth is in its simplicity. It's not a really complicated scheme, but he had to have a very creative mind to think of it in the first place, and he did. So we learned something from this, and this is something that we want to keep in mind for our students too, because sometimes our students may think, well, you know, I'm pretty good in math, but I'm not great. I could never be a mathematician. Oh, I could never be an engineer. You know, I like math. I'm kind of good at it, but I'm not great. No, I couldn't do that. But, you know, we learned something from Eratosthenes. Eratosthenes wasn't considered by his contemporaries to be a top-notch scholar or mathematician. They called him Beta. This is a true story. And yet he made a sizable contribution to mathematics, geometry, civilization in general, more so than any of his critics, that's for darn sure. And there's a point here for our students. Our students don't have to be the best at what they do in order to belong to their chosen field, in order to be successful, and in order to find their niche in life. They don't have to be the best. They just have to do their best and be reasonably good. Eratosthenes wasn't considered to be among the best mathematicians of his era, but his mathematical genius was certainly augmented by his broad background and his expertise in these other areas, and also by his creativity, which is something that intelligence tests don't measure. So just like Eratosthenes, our students don't have to be the best. They just have to do their best. And there will be a place for them in mathematics. And this is a huge lesson that we want to pass on to our students. They don't have to be the best. They just have to do their best. And there will be a place for them. And you know what? It will be a place that they'll enjoy being. Well, I hope you've enjoyed this retrospective of the course. And please do remember these points. They'll affect the way we teach. They'll also affect the way that we mentor our students. And again, the pleasure has been mine.